Hey everyone, Mr. Voikin here, and we are on lesson 7, almost at the end of this unit, and we're looking at some further factoring. It says, now let's take a look at this note. It says, if you have a perfect square trinomial. Now we've already looked at perfect square binomials, and we can split those into two binomials, but this is a perfect square trinomial. Now remember that a trinomial looks like this: ax squared plus bx plus c, where a is a number, that's supposed to be bx is and b is a number, and c is also a number. So in here it says that the first and last terms must be perfect squares. So what that means is you must be able to take the square root of a and the square root of c and get a whole number. Okay, and then the middle term, it says, must be twice, and twice means times 2. The product means the answer to multiplication of these square roots of the first and last terms. So what that really means is you're going to take the square root of a, multiply it by the square root of b, the square root of c, then multiply that by 2, and that will equal the b. Okay, so let's just try example A and see if that is true. So I'll resize this one, put it over here. Now we have, in example a squared plus 4a plus 4. Note that the square root of the number in front of a is going to be the square root of 1, which is 1. And when I take the square root of c, which is 4, it's going to be 2. So it's 1 times 2, and multiply that by 2. So we basically get 2 times 2. And yes, that does equal 4, which is that middle term. So in this case, it is a perfect square, where we would break it down into two binomials. A, the signs are the same, they're both positive, and that second term in each binomial would be 2. And again, to prove that this is correct, you could just expand this out. A times a is a squared, a times 2 is going to be plus 2a, 2 times a is plus 2a, and 2 times 2 is positive 4. And after collecting like terms, we have exactly what we started out with. So we know that it is a perfect square. Okay, so let's look at B. Is B a perfect square? Trinomial? Well, it is not, and that's because if we look at the number in front of the x, it's a 1, so that's true, but 6 is not a perfect square, so this entire thing is not a perfect square trinomial. Move on to C, and C says the square root of 4 is 2, and the square root of 81 is 9. 9 times 2 is 18. Multiply that by 2, and we get 36, which is that middle term. So in this case, that is a perfect square. Example C would break down into two binomials, and it's going to be 2x, 2x. The signs are the same, they're both negative, and the last term would be a 9. And again, what we want to do is expand that out to see if it is true. So 2x times 2x is 4x squared. 2x times negative 9 is negative 18x. Negative 9 times 2x is negative 18x. And negative 9 times negative 9 is a positive 81. Collect like terms, and you can see that we have proven that that works. Okay, now let's move on to D, and D says y squared. Remember, there is a 1 in front. Take the square root of 1 is 1. That's good. The last term, is a 16. The square root of 16 is 4, so that's good. The only thing is that you cannot make this into a perfect square because that sign is negative. It needs to be a positive sign there. Okay, so that is not going to work. All right, class example 2. Fill in the blank so that each of the following is a perfect square trinomial. So we just need to revisit that rule and follow the rule to ensure that we have the correct middle term. First thing we should do is always just check, is it a plus? Yes. 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 So each of those could technically be a perfect square trinomial if it follows the other rules. So what's in, on example A, what's in front of the x is a 1. So the square root of 1 is 1. And the square root of the third term, c, is going to be 10. So 1 times 10 is going to be 10. And we want to double that. So we're going to end up with 20. So that term in the middle is going to be 20. The part B is exactly the same. It's just that it's got a negative sign right there instead of a positive. So again, that will also be 20. It's this last positive right here that cannot be a negative, but this one right here is fine to be negative. Okay, let's look at C. And is 25 a perfect square? Yes, it's 5. Is 36 a perfect square? Yes, it's 6. 5 times 6 times 2 is going to be 60. So our middle term is 60. And part D, they're throwing a little curveball at us. They said, let's figure out that third term, C, rather than the middle term. A couple extra steps may be involved in that, but it's still the same theory. So what I want to do is just think what we're doing. Remember, it's going to be the square root of A times the square root of C times 2, and that's going to equal B. So as long as I can lay that out like that, I can now just substitute some values. So what is the square root of A? Well, that's the square root of 9, which is 3. What is the square root of C? Well, we don't know that, so that is the square root of C. And 2 is just a 2. And what is the middle term? B, it's 24. Now on this section right here, I can sort of do a little bit of math right here and multiply. This is 3 times root C in the middle times 2. So I can simplify that to 6 root C. And we still make that equal to 24. Now to separate the 6 from the root C, I'm just going to divide by 6. Divide by 6. That will cancel the 6's on that side, leaving a root 6 equals 24 divided by 6 is 4. But I want to know what C equals, not what root C is. So when I have root C, to convert that to C, what I'm going to do is I'm basically going to square that. And if I square the left side, I need to square the right side. So we end up with C equals 16. So you can see there's a little bit more work in there. So let's just confirm that we're correct. Following the rules from example 1 on D, we should be able to break that into 2 trinomials. The first term will be 3m and 3m. The signs are the same. They are both positive, and the last term should be 4. Now we're just going to expand that. 3m times 3m is going to be 9m squared. 3m times 4 is plus 12m. 4 times 3m is plus 12m. And 4 times 4 is a positive 16. Combine terms, put in descending order, and you've got the exact same thing that we started with, confirming that our math was correct. Okay, example 3, what do we have? Just says factor these. So I guess we're trying to continue on with the perfect square trinomial, so let's check. I got a positive sign, good, a positive sign, good, a positive sign, good. Can I take the square root of 49? Yes. And can I take the square root of 1? Yes. And if I take the square root of 49, that's going to be 7, and the square root of 1 is 1. If I multiply that by 2, I get 14, which is that middle term. So that confirms it's a perfect square trinomial. So letter A should break down into our two binomials. That will be 7x, 7x. The signs are the same. They are both negative, and they are going to be 1 and 1. And that one is done. Let's resize that. Take a look at B. Now, I guess they're just trying to change things up a little bit. It's not in the form that we're that we normally see. It's in ascending order instead of descending order, but I can just rearrange that into descending order if that makes it easier on you. So I'm just going to take this positive 25x, put it at the first, the positive 40, that's 25x squared, sorry, and positive 40x, and finally a positive 16. Now I'm going to just check, is it a positive at the end? Yes. Can I take the square root of 25? Yes, it is 5. Can I take the square root of 16? Yes, it is 4. Multiply that together and we get 40, confirming that it is a perfect square trinomial. Again, this is example B. So I should be able to put that into two binomials with a 5x. 5x, signs are the same, they're both positive, and the square root of 16 is 4, and there we go. Okay, so example C, they're just putting a fraction in there for us, but again, I can just check, is 1 over 9 a perfect square? Now remember from previous units this year, when we're looking at is 1 over 9 a perfect square, it's the same thing as the square root of 1 over the square root of 9. And we know the square root of 1 is 1 and the square root of 9 is 3. So yes, it is a perfect square. And we know the square root of 9 is 3. So it seems to follow all the rules so far. But let's see, if I multiply 1 over 3, times the square root of c, which was going to be 3, and then double that, will that equal what we have in the middle, which is 2? So 1 over 3 times 3 is actually 1, and 1 times 2 is 2, so yeah, it's real. So let's just break that up into two binomials. The square root of 1 over 9 was 1 over 3, and it's a, so 1 over 3 and a. The signs are the same, they are both negative. And the square root of 9, and don't forget there's a b squared right there, is going to be 3b and 3b. So this one was a little bit more complex than the other one, so let's expand it just to verify that we're correct. So 1 over 3a times 1 over 3, a is 1 over 9, a squared. 1 over 3a times negative 3b is going to be a negative ab, and negative 3 times 1 over 3a is another negative ab, and negative 3b times negative 3b is going to be a positive 9b squared. Collect all like terms and put in descending order and double check with our original. Ole. Okay, let's take a look at the next example, class example 4, factor completely. So let's see if these are continuing on with perfect square trinomials. Definitely not on the first one, we got a negative sign. Not on the second one, we got a negative sign. Although we got a positive sign, 14 is not a perfect square, so none of those are going to be perfect square trinomials. So Looks like, what are they doing? They're, instead of a being an a squared, looks like we got a to the power of 4, and we can't factor out any a's. But what we want to check in this case is that that is double that, and they are even, or the first one is even. So looks good right there, and on this one looks good, and on that one looks good as well. So now we just got to follow the other sort of methods that we've learned to begin with. Let's just get this done. So basically I want to take the number in front, which was 1, and multiply it times the 14, and we get 14. 14 breaks up into 1 and 14, 2 and 7, and the signs are different. And so we're going to subtract them, and it should equal 5. So 7 minus 2 is going to be 5. And the larger number, which is the 7, is going to be negative, indicated by that negative sign, and the other one will be positive. So when I break these up into two binomials, because of this 4 here, that has to be a squared and a squared. Again, the signs are different, so negative and positive, and the 7 went with the negative, and the 2 went with the positive. And as we've got this new sort of structure right here, we will expand this. So a squared times a squared is a to the power of 4. A squared times 2 is positive 2a squared. Negative 7 times a squared is negative 7a squared, and negative 7 times 2, a positive 2, is a negative 14. And combine like terms, and we get a to the power of 4 minus 5a squared minus 14, which is exactly what we started off with. So it looks like we're doing it right. Okay, we will resize this one, put it to the left, and move on to B. So the same thing. 1 times 5 is 5. 5 can break down into just basically one thing, and that's 1 times 5. And the signs are different. We're going to subtract equal 4, and the larger number is going to be positive. So 5 minus 1 is 4. That's true. 5 is positive, the 1 is negative, and again 4 and 2, they are double each other, so this will work out with an x squared. Signs are different. The 5 goes with the positive, the 1 goes with the negative. Okay, easy peasy, lemon squeezy. Let's move on to C. Okay, so example C, I now have x to the power of 6. But again, it's going to be that 1 times the 14, which is 14. Break that up into 1 times 14, 2 times 7. The signs are the same, and they're going to add in this case. So this tells me the signs are the same, should add together to be negative 9. So 7 and 2 is 9, and they're both going to be negative. So again, I should be able to break this one. Let's move you over here. Let's move that all over here. Okay. I should be able to break this down into two binomials, and they should be x to the power of 3 and x to the power of 3. The signs are the same. They are both negative, and the numbers we're putting in there are going to be 2 and 7. And to verify it, again, you would just expand that out, and you should get back to our original to verify that you did it correctly. All right, here we are at example 6, and it doesn't look like anything new here. It's just saying factor this one. So let's do that. 8 times 3 is going to be 24. And we're going to break 24 up into 1 times 24, 2 times 12, 3 times 8, 4 times 6. The numbers are going to subtract. The signs are different. It's going to equal 10, and the larger number will be positive. So 12 minus 2 is going to be 10, and the 12 will be positive, the 2 will be negative. Make reference that the exponents are raised to the power 4 and raised to the power 2, so they're half of each other. That's good. So I can't pull out any other numbers, so we're going to have to just keep the first one the same, which is 8x to the power 4. Keep the last term the same, -3. Break up the middle term into a, looks like -2x squared and a positive 12x squared. And we're going to split that up and pull something out of the first one, which will be looks like we'll pull out a 2x squared, and that will leave us with a 4x squared minus 1 on the inside. Let's move this guy over, indicating that we should end up with a 4x squared minus 1 if we can find something common to divide both those terms by. So -3 divided by 3 is 1, that's correct. And if I take 12 divided by 3, we get 4x squared. So that's good as well, indicating that we are going to pull out that positive 3. And now I just use these two to construct the first binomial, 4x squared minus 1, and I'm going to use that one and this one to construct the second binomial, which is 2x squared plus 3. Okay, and now we should move on to example 7, but there is no example 7. It seems to be missing, at least in my book it is, so we're moving on to example 8. So factor it completely. So I'm down to a binomial here in the first two examples, actually, and in the third example. And I can't really, when looking at the first one, I can't really pull out something common other than 1. So what I want to do is check to see if it's a perfect square. Now with the perfect square trinomials, remember the last term had to be a positive. But with a perfect square binomial, we do want that to be negative. So that is true, indicating that this should break up into two binomials, which would be k squared minus plus 1 and 1. So the first term was constructed by taking the square root of that, the square root of that, and making the signs different. Okay, so again, just verify k2 times k2 is k4. k2 times 1 is plus k2. Negative 1 times k2 is a negative k2. And negative 1 times 1 is going to be a negative 1. The two middle terms are going to be canceling each other out, and we finish with k4 minus 1, which is what we started out with, so we are correct. Okay, now what about B? B states that we got 80 minus 5 x to the power of 4. So I'm just going to spin this thing around. So I've got a negative 5x to the 4. No, I'm just going to leave it the way it is. We'll leave it like that. I can see that we can pull out a 5 in both cases. Okay, so we're going to have 80 divided by 5, which is going to be 16. Okay, so if I divide this one by in B, I'm going to pull out a 5, and I'm going to be left with 16 minus x to the power of 4. Okay, and right now it should work out okay, where we're going to, well, you know what, I think I will spin it around here. So instead of pulling out a positive 5, I'm going to pull out a negative 5, sorry. a -5. And that means that 80 divided by -5 is -16, and negative 5x to the power of 4 divided by 5 is going to be a positive 1x to the power of 4. And we're just going to rewrite this in descending order, where it's going to be x to the 4 minus 16. That makes a little bit more sense for us. And I've still got that -5 out there, and I should be able to break this into two binomials, because the square root of this 1 that's there is possible, the square root of 16 is possible, and we have the negative sign within this binomial. So this should break down into x squared, signs are different, and the square root of 16 is 4. And again, how do we check? Well, we expand it. I'll leave that up to you to verify that if you want. And let's move on to the last example here, which is C. So let me just move this out of the way so we can see our original answer while we're working, or question while we're working. Okay, C. So can we pull anything common out of this? Well, I'd say a 2, a P, but we can't pull out that Q. So we can pull out a 2 and 1P. So I'll pull out a 2P. What am I left with? A P to the power of 4, a Q to the power of 4, minus, and 162 divided by 2 is going to be 81. And I pulled out a P, so that P is gone, leaving us with T to the power of 4. Okay, so the number in front of the first term is going to be 1. I can take the square root of that, and I can take the square root of 81, and that is a negative sign within this binomial. That tells me this is a perfect square binomial. So we're going to pull out that 2p originally that we had and formulate two binomials out of this. So this would be a p squared, q squared, p squared, q squared. Signs are different. And the square root of 81 is 9, and the square root of t4 is t squared. And there you have it. Okay, well, that's it for this lesson, and we're getting near the end of the unit, which is great. And as usual, here is your at-home assignment to bring to our next class. A is 4x squared minus 44x plus 121. B is 2a to the power of 4 minus 5a to the power of 2 plus 2. And the C is a to the power of 4 minus 256 b to the power of 4. And what you need to do with all three of these is factor them out. And don't forget to verify that you're correct by expanding them out and comparing them to the original questions. And then when you come to the next class, we'll be working on our in-class assignment, which is going to be on page 368 through 372, questions 1 to 13. See you next class.